Dear viewers, you are my greatest inspiration. You have supported me all these years. Your kind words of appreciation motivate me to keep making more videos. This video lecture presents an in-depth exploration of the key role of Bragg's work alongside Laue's work, starting with the historical context, core principles, a comprehensive review, and intricate conceptual analyses of the X-ray diffraction and X-ray scattering, theoretical as well as mathematical aspects, and how it revolutionized the field of structural biophysics and particle waves. This video lesson is a compact information guide, in the form of your ready exam answer paper. Prior to watching this video lesson here, in order to fully comprehend the relevant background, and to satisfy your curious mind, viewers are advised to watch my earlier video lectures on elaborate conceptual recount of light diffraction and interference, Rayleigh scattering, crystal system, and Thomas Young's double-slit experiment. Please find the links in the description below. As we all know, wave is an undulatory phenomenon, a disturbance so to speak, that propagates through space and time, and is regularly repeated. X-ray is a form of electromagnetic radiation of high energy and very short wavelength, which is able to pass through most materials that are opaque to light, for example, human body, hence widely applied in medical imaging. Crystals are composed of three-dimensional patterns. These patterns consist of atoms, or groups of atoms, in ordered and symmetrical arrangements, which are repeated at regular intervals, keeping the same orientation with respect to one another. Let's start with this most simplified one, a cubic crystal system, with unit cell dimension, A. Here's a non-cubic system with unequal dimensions or parameters. A diffraction pattern is obtained by measuring the intensity of the scattered waves as a function of scattering angle. Peaks intensify as the number of rows increases in a very similar manner to the diffraction peaks from a diffraction grating as the number of slits increases. As you have already learned from my earlier elaborate video lecture, diffraction refers to the scattering of waves around obstacles or apertures, and the spreading out of wave fronts from a chromatographic grating, which results in diffraction pattern. This is what we are going to discern in the context of Bragg's law as well. Please note that X-ray diffraction is often considered a subset of X-ray scattering, where the scattering is elastic and the scattering object is crystalline. In order to discern X-ray scattering and X-ray diffraction, one has to relate to the concept of light scattering. Well, light scattering is defined as a phenomenon of deflection or deviation of light beams from its original course of trajectory caused by irregularities in the propagation. As a result of collision with medium particles and interactions with inhomogeneities in a medium. This phenomenon is responsible for various natural effects, such as the blue sky, white clouds. A typical example is Rayleigh scattering. You must have noticed that I make a point saying Bragg's instead of just Bragg, to show respect for the historic research works of both the father and the son, and their individual contributions. The culmination of structural studies in the history of experimental physics was the historic breakthrough by Watson-Crick double-helix DNA structure housed in the Cavendish Laboratory when Lawrence Bragg was the director of the Cavendish Laboratory, Cambridge. Biotechnology, crime detection, forensic science, recombinant DNA. None of these would be possible if Watson and Crick had not discovered DNA structure using X-ray diffraction. The specular reflection of X-rays. This is the original historic publication of Lawrence Bragg in Nature, back in 1912, still available online for ardent readers. The core principle launching the discovery and formulation of Bragg's law. The Bragg condition is satisfied when the reflected waves are in phase. If the emerging reflected waves have opposite phase, no reflected intensity will be observed. That is to say, Bragg's law and Bragg conditions are not fulfilled. When the angle of incidence of the X-rays does not satisfy the Bragg's law or Bragg conditions, the emergent beams are no longer in phase and cancel each other. No reflected intensity will be observed in such a situation. Here you see a simplified illustration of two-dimensional representation of evenly spaced discrete virtual set of parallel atomic planes in crystal lattice. Repetitive periodic array of atoms, all the Xi are denoted by a series of blue globules. The planes are at distance d apart. Incoming X-ray beams of wavelength lambda, shown in yellow color, impinge upon a crystal at an angle of incidence theta. They are subsequently reflected from the atoms with the same angle theta. The emerging beams are shown in fuchsia color. The direction of normal to the planes is denoted by white dotted line, whereas incoming and outgoing wavefronts are illustrated in this diagram with respect to the normal. Here you see a typical example of an arbitrary situation, where the waves have phase match, peak-to-peak alignment, denoted by dashed lines. Here you see another situation where the waves are out of phase. When the orientation of the in-phase incoming waves meets the conditions of geometric orientation with respect to the virtual atomic plane mirrors, that is to say, the Bragg conditions are satisfied, the so-called reflected X-ray waves will be in phase. The two incident component beams X1 and X2, shown in yellow color, define the wavefront AD. The two emergent component beams X1 and X2, shown in magenta color, construct the wavefront CD. Taking this into consideration, that cooperative scattering is occurring, these two component beams X1 and X2, that construct the wavefront AD, are in phase. These two component beams X1 and X2, that construct the wavefront CD, are in phase as well. In order to obtain a cooperative effect, after reflection, both X-ray beams should still be in phase. This is a situation that will only occur if the path difference traveled by the wavefronts, before and after reflection, corresponds to an integral multiple of wavelength, as shown in this example. The X-rays reflecting from two successive planes must interfere constructively to form an interference pattern. Otherwise, the X-rays would interfere destructively, which means no pattern. In order for constructive interference, the difference in path length between the beams must be a whole number of wavelength. By observing the interference pattern, the internal structure of the crystal can be deduced. Here we are gonna derive Bragg's law by applying specular reflection geometry and basic trigonometry. Applying basic geometry, total deflection from the original incoming direction of the incident radiation is 2 theta, which is the total deflection angle, shown by white dotted curve. Here we have illustrated a simple system with a set of 3 evenly spaced discrete parallel virtual atomic planes within a crystal lattice, shown in blue color. The lattice spacing parameter d is constant, shown in bright green color. 1 top layer, 1 middle layer, 1 bottom layer. Incident waves, shown in yellow color, impinge upon the crystal atomic planes at an incident angle theta. The scattered waves, shown in fuchsia color, are generated following the geometry of specular reflection, that is to say, scattering angle is theta as well. The extended dashed line in yellow color is drawn to indicate the original incoming direction of propagation of the incident waves, making an angle theta with respect to the atomic planes. Wave beam number 1 is incident upon the top plane, while wave beam number 2 penetrates through and strikes the second plane. This simple schematic diagram is based on the laws of specular reflection using the analogy of mirror reflection geometry. Here we are taking into account wave beam 1 and wave beam 2, emerging from 2 adjacent or successive atomic planes. Here we have drawn the wave fronts. They are, by definition, represented by the lines perpendicular to the direction of the wave propagation. The incident wavefront is shown by the dotted line in yellow color, and the outgoing scattered wavefront is shown by the dotted line in fuchsia color. Needless to say, that wave beam number 2 has obviously traveled a longer path, compared to that traveled by the wave number 1. The extra path traveled by the incident beam, that collides with the inner plane, as well as the extra path traveled by the scattered beam emerging from the inner plane, are shown in solid line segments in red color. Based on the trigonometric functions, each of those extra segments, as shown in red color, are d sine theta. That is to say, the total extra path traveled, or path length difference between wave beam 1 and wave beam 2 from adjacent or successive atomic planes, would be d sine theta plus d sine theta. Here we have illustrated a simple system with 2 evenly spaced virtual discrete parallel atomic planes within a crystal lattice. The lattice spacing parameter d is constant, shown in bright green color. The imaginary atomic points or loci are represented by blue globules. 1 top layer, 1 bottom layer. The incident waves of wavelength lambda, shown in yellow color, impinge upon these atomic planes at an incident angle theta. Let's say, incident wave 1 hits atom A, whereas incident wave 2 hits atom B. The scattered waves are shown in fuchsia color. Here you see the incident and scattered wave fronts. Please observe the geometric context in this arbitrary example carefully. With this wavelength lambda, for lattice spacing d, and for this particular incident angle theta, in this particular case, the extra path traveled by the incident beam onto atom B of the bottom plane happens to be 2 full rounds of wavelength, as illustrated in the diagram. No decimal. No fraction. Likewise, the extra path traveled by the scattered beam, emerging from atom B of the bottom plane, happens to be 2 full rounds of wavelength, as illustrated in the diagram. No decimal. No fraction. Please bear in mind that this is an arbitrary example for the sake of better clarification of the geometric context. Modifying the wavelength and the angles would undeniably alter the extent of this extra path, as well as the path length difference between the emergent beams from adjacent or successive planes. So, now you realize precisely how to conceptualize Bragg's diffraction law based on fundamental laws of optics, geometry, and trigonometry. Defined by the geometrical construction of the incident wavefront AD and the reflected wavefront DC, this geometrical representation clearly shows that the total extra distance covered by the X-ray beam 2 is AB plus BC. As the two X-ray beams 1 and 2 are in phase, the total path difference ABC would be an integral multiple of the wavelength of the X-ray. Here, let me clarify the geometric context even further. The triangle ABD, shown in bright red, is a right-hand triangle. The side AB is opposite to the angle theta. DB is the hypotenuse of this right triangle, and it's equal to the lattice spacing D. Here is an interesting aspect for ardent viewers. The concept utilized to derive Bragg's law is similar to that used for Young's double-slit experiment. Viewers are advised to watch the elaborate illustrated conceptual analyses in my earlier video lesson on Thomas Young's double-slit experiment in order to fully comprehend the equivalence and correlation between. along the direction X, wave vectors k represent the incident X-rays, as shown in yellow color, and impinge upon the two atoms on the aforementioned oblique lattice plane, at an incidence angle theta. On the other hand, along the direction x', wave vectors k' represent the scattered X-rays, as shown in fuchsia color, and are scattered from those two atoms at a scattering angle theta'. For now, as a working example, let's consider a one-dimensional row of evenly spaced discrete lattice points of a crystal. Here, as depicted in the diagram, it happens to be a simplified segment of one of those arbitrary oblique lattice atomic planes. What we realize is, first of all, no fractional cooperative dispersion orders can occur. Furthermore, provided that this incident angle is maintained constant, this equation would also be valid for any scattered beam that happens to emerge with this same scattering angle from the target atom. What would that imply? What would that lead to? Let's see what it's gonna look like. In multidimensional cases, considering several rows of atoms, in any periodically ordered three-dimensional distribution of atoms, these equations are fulfilled simultaneously, and cooperative scattering from such systems would result in discrete diffraction lines. Therefore, all scattered beams around the row of atoms, with the same scattering angles, would fulfill these equations, and would form a conical surface, coaxial with the row of atoms. Like this.
Ready lecture notes and study materials are available on request. Please use the comment section below for further academic discussions. Viewers' suggestions and ideas of new video lesson topics are gratefully appreciated. Stay tuned for more uploads. Please remember to like, subscribe, share.